Good morning, everyone. My name is Ayman Alswaitti, and today I will be presenting our research titled An Eco-Friendly Brucite-Based Geopolymer Adsorbent for Dyes and Pharmaceutical Compounds Removal from Aqueous Solutions. This work was conducted by Ahmad Ayman, Abdulrahman Ayman, and myself under the supervision of Dr. Omar Najm and Engineer Esraa Hijah at Al Ain University in Abu Dhabi. I will first start with a brief introduction about the water pollution problem and the need for sustainable adsorption material. Then, I will present a short literature review highlighting previous research on geopolymer-based adsorbents. After that, I will explain the main objectives of our study and its novelty. Next, I will describe the methodology used in this research. Then, I will discuss the key results obtained from the experiments. Finally, I will conclude with the main findings and future prospects of this project. Water scarcity is becoming a major global issue, and it is estimated that around 40% of the world's population will suffer from water scarcity in the next 30 years. At the same time, wastewater contaminated with dyes and pharmaceutical compounds poses serious environmental and health risks. Some examples of the toxic dyes and our research is about these two dyes. Methylene blue, also known as MB, it has biological uses and used in cancer treatments. The second dye is malachite green, also known as MG. It also has biological uses and textiles. Currently, activated carbon is the most commonly used adsorbent for wastewater treatment. However, it is expensive and not fully sustainable. Therefore, there is a strong need for cost-effective and eco-friendly alternatives. In this study, we explore the use of geopolymer concrete as a sustainable adsorbent material. But the main issue in geopolymer concrete is NaOH. It is toxic and not sustainable. Also, not cost effective. So, in this study, we replaced NaOH in the production of geopolymer concrete and using it for dye removal, and this serves SDGs 6 and 11. Previous studies have shown that geopolymer concrete used fly ash-based geopolymer spheres and rice husks, metakaolin, and GGBS geopolymer, also acid protonated treatment of the synthesized geopolymer, and lastly, they all used caustic soda, also known as NaOH, in the geopolymer preparation. The main objective of this study are to use brucite-activated geopolymer concrete as an adsorbent, to study the effect of contact time on dye removal, to determine the optimum adsorbent dosage and particle size, and to analyze the adsorption behavior using kinetic isotherms. The novelty of this work lies in exploring brucite-activated GGBS geopolymer as a new and sustainable adsorbent. This approach combines environmental benefits, low cost, and high adsorption efficiency, which has been not widely studied before. Now, moving on to the methodology, this includes the material used, experimental setup, and analytical techniques applied to support all research objectives. The materials used include GGBS, brucite and sodium silicate, two cationic dyes, malachite green and methylene blue, and geopolymer powder. The experiments were carried out using amber glass bottles with Teflon caps to avoid light interference, glass syringes and filters, and cuvettes for testing, and the equipment used a UV vis spectrometer and an orbital shaker. Experimental methodology. First batch reactor where we use glass bottles with Teflon caps in amber color. Our targeted performance is the removal percentage both MB and MG. We use different dye concentration of 50, 25 and 10 ppm. The adsorption mechanism was it pseudo first order or pseudo second order. Lastly, to analyze the adsorption behavior using kinetic isotherms to see whether it's Langmuir model or Freundlich model. In this section, I will discuss the results in terms of removal efficiency, adsorption mechanism, and kinetic behavior for both dyes. In the legend of the graph, Each color represents a particle size and a dosage. For example, the color orange is 300 micrometer in size and 0.2 grams for the dosage. At 50 ppm concentration, higher adsorbent dosage and smaller particle size gives us the optimal removal for MB. And as for mg, it reached nearly 100% removal within the first 15 minutes, which tells us that our adsorbent works perfectly with mg. At 25 ppm, a similar trend was observed, confirming the effectiveness of the geopolymer adsorbent across different concentrations. At 10 ppm, near complete dye removal was achieved, indicating a strong adsorption performance at a low contaminated concentration. For MB, the kinetic analysis showed that R2 in the pseudo first order model nearly reaches 1, which is what we want. Also, the pseudo second order also nearly reaches 1, but the first order has better results, so the pseudo first order fits the data better, indicating that there is a possibility it is physisorption. But for mg, the story here is different. Both the pseudo first order and the second order reached in R2 1, which tells us it can be both physisorption and chemisorption. How to know which one is it? We go to the kinetic isotherms. In the legend, we have our data in blue dots and Freundlich model in orange and Langmuir model in green. Isotherms analysis for MB shows us that Freundlich model fits our data better, which means multilayer adsorption, which confirms physisorption. And for MG, our data shows that Langmuir model fits it better, which means it's monolayer adsorption, which confirms it was chemisorption. When compared with previous studies, the proposed geopolymer adsorbent shows improved removal efficiency while maintaining better sustainability at a lower cost. Concluding remarks and future prospects, our main conclusion and the future prospects. In conclusion, brucite activated GGBS geopolymer was successfully used in dye removal from aqueous solutions. High dye removal efficiency was achieved in short time period. Mg followed chemisorption and monolayer behavior, while Mb followed physisorption and multilayer behavior. And it is a sustainable and cost-effective, and it's an alternative adsorbent. Future work will focus on heavy metal removals applications and make water filters for pharmaceutical removals. Thank you for listening, and any questions? These are the references we used. If you have any question regarding the results, please feel free to ask.